All right. Don't worry, today is going to feel like review.
Is that why so many people are falling asleep?
So many people are falling asleep? Is that what you just said?
This is excellent.
You heard it, Donnie.
Okay. 5C.
What about I'll read it? No, you won't.
Michael.
Oh, wait. Okay. Breaking.
That's the one after 5B.
Yeah, I see. I was gonna read 5C2. Breaking bonds requires energy, and making bonds releases energy.
Everybody know that. Yes, we do.
Yes, we do.
Smarter than we actually are.
Wait, who said what?
All right, well, let's read two more things, and then you're going to see, oh, yeah, we did know that. 5C1. Tia. Birthday girl.
Potential energy is associated with a particular geometric arrangement of atoms or ions and the electrostatic interactions between them.
Intermolecular forces?
Well, this is atoms or ions, so we're talking about intramolecular force. We're talking about my
IMFs.
fifth best friend.
Coulomb's law.
Coulomb's law.
Yeah. What about the law of gravitation?
Yeah, no, spreadsheets are fourth.
Things change.
Logan, Oliver, my wife.
Oh, Oliver's number 2 now?
Logan's the favorite child.
Right now, he's the one that can talk.
He can
Spreadsheets, Coulomb's law, Maxwell
talk.
Boltzmann.
What he does.
So what happens when you
Hey, what about the law of gravitation?
one day? No, you don't have favorite child. You love them equal.
Well,
Okay. Hey, Myra.
The attraction between the electrons of one atom and the protons of another explains the tendency for the atoms to approach one another. The repulsion between the nuclei or core electrons explain why the atoms repel one another at a close distance. The distance at which the energy of interaction is minimized is called bond length, and the atoms vibrate about this position. I had some problems. Forgot how to read first.
Now, if that doesn't sound familiar, part B.
The moon.
Hope, read us B.
A graph of energy versus the distance between atoms can be plotted and interpreted. Using this graph, it is possible to identify bond length and bond energy.
Yes, does that sound familiar?
No.
Let me refresh your memory from Big Idea 2. The formation of a nonpolar covalent bond can be represented graphically as a plot of potential energy versus distance for the interaction of two atoms. Right?
Yeah.
This is Big Idea 2. We talked about it. Somebody said, oh yeah, those graphs.
Where the rock rolls
Yeah.
Oh,
Yes. The Lennard-Jones potential diagram. What does it tell us?
potential energy as like distance between
Well, it tells us that, well, I guess let's go back and think about this simulation, right? We've got these arrows, these orange and pink arrows. What do those represent?
Attraction and repulsion.
Attraction and repulsion. The orange one is the attraction, that's why they're pointed towards each other. The pink is the repulsion. Now I think we just read, why would atoms attract each other? Who read A? Who read A?
Myra.
Myra, read the first sentence of A again, please.
The attraction between the electrons of one atom and the protons of another explains the tendency for the atoms to approach one another.
Right? So we're talking about sharing electrons. It's the nuclei of one atom attracting the electron of another atom that makes that bond. If we draw it with the Lewis structure like this, we draw those electrons in between the two atoms to remind us that the nuclei of this is going to be attracted to those shared electrons. The nuclei of this one is going to be attracted to those shared electrons. Wipe that nasty frown off your face. Okay, but that's the orange arrow. What's responsible for the pink arrow, Myra?
The repulsion between the nuclei explains why the atoms repel one another at close distance.
Okay, so we can't just get these things closer and closer and they keep attracting stronger and stronger and stronger, because eventually the core electrons start to repel if they get too close. The nuclei will start to repel if they get too close. So we'll see that pink arrow growing and growing and growing. If they're too close together, the pink arrow is larger than the orange arrow. If the pink arrow is longer than the orange arrow, that means we're in a repulsive situation. When I hit play, they're going to move apart, okay? Now, really, I should have put them so close that they're like here, and they would zing, fly away, right? Okay. But as long as we have attraction greater than repulsion, they're going to attract. Okay, what happens at the bottom of this graph?
That's like
At the very bottom point of this graph, the force of attraction is exactly balanced with the force of repulsion. So if we could get those atoms to be exactly that distance apart, we look at the total force here. Oh, I'm not quite there. Maybe there. They're exactly that distance apart where we've completely balanced the attractive and repulsive forces. What's going to happen if I hit play? Nothing. It pretty much should stay there. Okay? But if they are a little bit further apart, the attractive force overwhelms the repulsive force. So in this case, they're getting pulled in closer. But if they get pulled in past that ideal distance, then the repulsive forces grow faster than the attractive forces, and now we get an overall repulsion. Okay, so we talked about how there is no such thing as a bond length in terms of like no bond is really just going to sit at that distance and just chill. They're always vibrating about that minimum potential energy. Osama.
So could you represent it with a simple harmonic motion, or would it be something else, like a trig function?
Probably. Well, I don't know exactly how simple it would be, because I don't think it's perfectly symmetric, this dip. Because the growth of the repulsion is not the same order as the growth of the attraction. Okay. Does this sound familiar?
Yeah.
Does this make a little more sense the second time around?
Possibly.
Finally get it! Okay. Well, it only took 6 months, but... All right. So, this is what we're talking about in B. A graph of energy versus distance can be plotted and interpreted. Using the graph, it is possible to identify the bond length. Where's the bond length?
It's that. It's right over there. It's right over there.
It's between the y-axis and the red line.
It's actually not this.
No, it's
Because this arrow stops here, but this is
it's from epsilon.
zero potential energy. It really should be, yeah, that arrow should go all the way up to where this little vertical epsilon line is. That distance from here to here, wherever that average distance that these atoms are in this simulation, that represents the bond length. It's the minimum potential energy. It's the point at which the attractive and repulsive forces are balanced. How about the bond energy?
That's the other. I don't know Greek letters, so I can't say.
Epsilon?
No sigma?
That's this fancy looking E, or a backwards 3. It's the difference between the minimum potential energy, which is what the atoms would have if they were that perfect bond distance, and an infinite distance where they are not feeling any attractions or repulsions. So the y-axis is telling us the bond energy, the x-axis is telling us the bond length. Potential energy. So bond energy is the y-axis. The difference between our infinite distance and our perfect bonding distance, that change on the y-axis is our bond energy. The green arrows, in this simulation I can actually adjust it. So I can make a stronger bond here. I can pull this thing down, and notice on that slider on the right, the interaction strength goes up. Right? So this is a stronger bond. I can also change the bond length by making larger atoms or smaller atoms. That changes the x-axis. Or I can slide the atom diameter. Yeah, I did it custom. That's fine. Okay? C. Hope.
Conceptually, bond making and bond breaking are opposing processes that have the same magnitude of energy associated with them. Thus, convention becomes important, so we define the bond energy as the energy required to break the bond.
So what they're saying is, if I take these atoms that are bonded at that perfect bond distance and I pull them apart, I change the potential energy by a certain amount. That would represent the energy required to break that bond, right? Here they were bonded, now they're not, I just broke the bond. However much I have to raise that potential energy, that's the bond energy. However, I can think about it as taking those things at an infinite distance, allowing them to come back to that perfect distance. Well, it's the same change in potential energy, right? But one of them causes an increase in potential energy, the other one causes a decrease in potential energy. So sign is important. One of them is going to have a positive energy change. Energy is going to have to go in for one of these processes. The other one, energy is going to come out. Which one releases energy?
Making bonds.
Making bonds. We know it releases energy because if the potential energy is decreasing, where's that energy going?
Kinetic energy.
It's being released.
Dang.
How does it get turned into kinetic energy?
Gamma radiation.
If I take these atoms that are very far separated and I allow them to come together, they vibrate about some minimum distance, right? But no bond is made in isolation. There's always going to be other atoms or molecules around. And what happens when that vibrating bond finds another atom or molecule?
About to punch her in the face? Looked like you were about to punch her in the face. Just.
I was going to. That was my thought, right? If I'm vibrating very, very quickly and I run into some bum that's just sitting there not doing anything, what's going to happen?
Put me out of my misery.
BAM! She's going to go flying, right?
And hopefully dying.
That's the point. Yeah. So vibrational bond energy is eventually converted into kinetic energy when particles go flying. Now I can show you that. The nice simulation I have here that I have to Osama, when I go back and watch this on YouTube and I hear all those little comments you're making, am I going to be happy or upset?
I think you might be entertained.
I think you might be mistaken.
I didn't know you were recording.
Okay.
Wait, now they just
all right, so we're going to look at a very simple reaction here. We got diatomic greens and diatomic blues. When I let this thing run, we see the particles have some kinetic energy to begin with, right? There's a little scale on the right. It looks like they don't have a lot of kinetic energy. They're moving pretty slow, right? Ooh, interestingly enough, who's moving faster? Green, why? Right? Remember the difference in Maxwell-Boltzmann distributions. We see an overall distribution of speeds, right? Some fast, some slow. But remember, the heavy particles, on average, are going to be moving slower than the light particles, okay? We see they're also all vibrating, right? Are they vibrating quickly?
Yeah. Quite.
Well, this one is. That one, not so much. This one, definitely not so much. It's just like, just a little bit. Okay? Now, in this simulation, what I have to do to get this thing to go is I have to add a spark. That spark breaks one of those bonds to get this reaction going, but watch what happens.
Oh my God.
Oh my God.
Look at that guy.
Oh Lord.
And watch what happens when this guy, who's really strongly vibrating, smacks into somebody else. BAM! Sent that thing flying. Look at the kinetic energy on the right.
Oh my God.
Is this what happened with mom?
Yes. A big rumble.
Woo!
Damn, there's that one atom just out of them.
That's me. Big blue.
Okay, so this is a simulation that shows us how bond energy can be converted into kinetic energy. Why, when I burn something, do the products end up hotter than when they started? Well, we're converting the potential energy, the bond energy in those chemicals, into kinetic energy of their products by the same sort of mechanism that we saw right here. Okay? Now, I can actually sort of show that if we think about our sixth best friend.
Newton's law of gravitation.
No, sixth.
Math,
Name
Maxwell
seven.
Boltzmann.
Leonard Jones potential.
What?
That is,
Oh!
where do I fall?
Seven is too many for us.
Yeah, where do I fall on this?
Where's Zishan?
You guys are not my friends.
I thought Dennis was fine.
But Facebook says differently.
You shouldn't take offense. We can't be friends.
Why?
Because I'm your teacher.
How about after graduation?
We can be friendly, but I cannot be your
You're
friend.
not friendly.
Yeah.
I said we can be friends. After graduation.
Zishan didn't graduate.
Okay. Now, I'm going to draw the blue one with a slightly shallower dip. Why?
Oh, bond length.
The
Bond
size.
energy.
Probably the size, right? If these are bigger atoms, they're not going to be able to get as close to each other, right? Coulomb's law says that's going to make for a weaker bond, okay? So what we're doing essentially is first we have to take these molecules and we have to break them apart. I added a spark. That broke one of them apart to get this process to occur, okay? Now, once this thing happens, the kinetic energy, if you watch this thing go, the kinetic energy of the products sometimes are so great, those vibrations are so great, that they can smack into one of those diatomic greens or blues and actually break it apart. So once the kinetic energy, once the potential energy is turned into kinetic energy, that kinetic energy can then break apart more bonds, right? So when we burn something, we just have to add that spark once, and then that overall release in energy creates the activation energy to keep that thing going, okay? But essentially what we have to do is we have to pull these atoms apart. And once the atoms are separated, we can allow them to combine in a new way. So I'm going to flip this graph over on the other side. Same graph, I'm just going to draw it now going this way, representing the products, like this, right? Because the product that we made, we saw because of its vibrations being so fast we must be making really, really strong bonds. Those green-blue bonds that were formed must be a lot stronger than the green-green or blue-blue bonds, blue-blue bonds that we broke. Okay? So conceptually, we can kind of think about like pulling these things apart and then allowing them to come back together. This is really just a mirror image of this, right? I could have drawn them all on the same graph. I thought it might be nice to draw it this way so you kind of get a sense of almost like we're talking about like exothermic and endothermic type reactions now, right? We're saying we're starting at a potential energy here. We have some activation energy that we need to overcome. But once we overcome it, we will have some decrease in potential energy to form our products, right? So now if we think about this path, it looks kind of like our energy profiles that we were talking about in the kinetics. Is there a question? Want to watch this thing go again?
Yeah.
There he goes.
Just
Forming those strong blue-green bonds, vibrating very quickly. Watch that guy in the bottom. Bam! Bam! That was pretty weak. Bam! Ooh, we hit that green, sent him flying.
which green is like? Hey, you can't follow.
Woo! Look at that guy in the middle. Did you see him? He's going crazy.
Oh
Okay,
God.
now he just transferred some of that wild energy that he had into some other molecule, sent him flying, giving that other molecule kinetic
Looks like
energy.
bullying.
Woo-wee!
Wait, I know that.
Cool.
This is one. Oh yeah, they're gonna shut up.
Okay, now, do we have two other parts to read? D, Deborah.
Because chemical bonding arises from electrostatic interaction between electrons and nuclei, larger charges tend to lead to larger strengths of interaction. Thus, triple bonds are stronger than double or single bonds because they share more pairs of electrons.
So yes, when we think about these Lennard-Jones potential diagrams, if I have something like an FF bond, and I'm going to compare that to an OO double bond, well, when we go back to our simulation here, in the FF, we only have 2 electrons being shared, right? In oxygen-oxygen, we have 4 electrons being shared. So Coulomb's law says the more electrons that are being shared, the more force of attraction this nuclei is going to experience towards those shared electrons, right? So if we're thinking about the magnitudes of the attractive and repulsive forces, I guess in this simulation, attractive are orange here. The attractions of oxygen are much stronger than the attractions in fluorine. Right? Coulomb's law tells us the more charges that are attracting, the stronger the force. The repulsions are probably going to be about equal. They have about the same number of core electrons. They have about the same number of protons in the nucleus. Fluorine has a couple of more. Okay, so maybe I could draw the repulsions of fluorine a little bit bigger than the repulsions of oxygen, okay? But if I drew these things the same distance away from each other, oxygen's forces are not balanced, right? At equal distances of atoms, because of those extra electrons in between the oxygens, these are actually experiencing a larger attraction. So are they going to stay at the same distance as the Fs? No. They're going to pull in closer until, remember Coulomb's law says the closer these things are, the larger those forces, okay? So the attractive forces are actually going to get even stronger. but the repulsive forces are going to get stronger as well, okay? So maybe at this even closer distance, now oxygen's overall attractive and repulsive forces are balanced, okay? But only at a shorter bond distance. So it's saying that larger charges tend to lead to larger strengths of attraction. Triple bonds are stronger than double. Double bonds are stronger than single. All right? And then E. Sleepyhead.
Which one?
Sleepyhead number 1. E.
Stronger bonds tend to be shorter bonds.
Stronger bonds tend to be shorter bonds.
Yeah.
For the reason I just explained, right? If there's more attraction pulling these things together, they have to be closer together to balance the repulsions. So a stronger bond is usually going to be a shorter bond. So if I compare neon bonded to neon, it just doesn't happen, versus oxygen bonded to oxygen, the distance is going to be a heck of a lot less. Okay? Now, that's all sort of the conceptual stuff. What are we going to do with this? Homework, yeah. We are actually going to use this concept of bond energies to make predictions about chemical reactions. In the last unit, we learned about calorimetry. Calorimetry is the process where we go in and we do some reaction or some change, physical change or something like that, and we measure the energy change associated with it by doing that reaction in the presence of usually water that can absorb the energy change. Right? We burned a marshmallow, we collected the energy released by that burning marshmallow with water. Because we can do an MC delta T for water, we can figure out what the change in energy was for the marshmallow. Okay, that's an experimental technique. But we can actually predict that same change in energy just by thinking about what types of bonds we have. Unfortunately for you guys, somebody did a whole bunch of work and actually measured how much energy it takes to break a whole bunch of different types of bonds.
Sat there with the thermometer.
Now, somebody said something about Hess's law. I actually just did Hess's law. Sort of. Well, we'll come back to Hess's law. Hess's law is going to tie us back to kinetics a little bit, and it's going to be the third way that we can actually calculate a change in energy. So, we could look at some sort of chemical reaction. Like my favorite. The old $10,000 shower.
Hey, did someone put that?
$50.
I think somebody put, I think the highest I saw was like 6,000.
Dude, I had $23 at first. I'm like, wait, what?
I got $50.
They probably didn't leak it.
Now, some people very wisely said, I just calculated it takes $60,000 to pay for the heat for my shower. That ain't right. I must have done something wrong.
Some of us don't know the value of money.
I'm bathing in the river. That's how much the showers.
I shower in Lincolnwood.
Yes, we could go in and we could burn methane. We could transfer the energy change for that burning methane into some water. We could figure out how much the water's temperature changed, MC delta T it, figure out how to change in energy for the combustion of methane experimentally. But we can look at what is actually happening. In this reaction, we have a carbon that is forming 4 single bonds to hydrogens. You got to be able to draw a Lewis structure to do this. There's 2 oxygen molecules. If you draw the Lewis structure for oxygen molecules, O2, you'll see they have a double bond. when we look at the products, we have CO2, which is a carbon doubly bonded to 2 oxygens. We have 2 waters, which are oxygens single bonded to 2 hydrogens. So, we have carbon-hydrogen bonds as reactant on the reactant side. We have no carbon-hydrogen bonds on the product side. So that means we're going to have to break all of these bonds. We have oxygen-oxygen double bonds on the reactant side. We have no oxygen-oxygen bonds on the product side. So we're going to have to break both of those oxygen-oxygen double bonds. Breaking bonds requires us to put in energy. So let's see how much energy we have to put in to break these reactants apart. Well, we've got 4 carbon hydrogens. That's 4 times, where's carbon hydrogen on the list? 413.
1652.
Now these are in kilojoules per mole.
It should be.
So let's say average bond energy, kilojoules per mole. So we can think about doing a whole mole of this reaction. We're going to have 4 moles of carbon-hydrogen bonds. So I'm going to multiply the energy of each times the 4 moles of bonds we're breaking. Right? I didn't put the 4 moles there. Okay. But so to break apart a mole of methane requires
1652.
1652, 1,652 kilojoules. We also have to break 2 oxygen-oxygen double bonds. That's 2 times
495.
495. You got to be careful. You have to draw a Lewis structure. If you don't draw the Lewis structure and you just assume O2 has single bonds, look at the energy of an OO single bond. 146. Remember, we just read that double bonds are stronger than single bonds. So we have to draw the Lewis structure so we know what type of bond we're breaking. 2 times 495?
990.
990 kilojoules to break apart my oxygen. So in total,
2642. Sounds right.
2,642 kilojoules of energy are required to break apart my reactant. Okay? Does this chemical reaction require me to put in 2,642 kilojoules? In other words, is the delta H for this reaction 2,642?
No.
No, why not?
You got bonds being formed.
Because we're going to get some of that energy out when we make our new bonds, right? Breaking bonds requires energy. So we're going to pull all these things apart, but then when we allow them to come back together, those new bonds that we're forming that are going to be vibrating very quickly might, well, they might break some of these bonds, providing some of this energy, but they might also get turned into kinetic energy and be released. Okay, so let's figure out how much we make. We've got 2
Carbon double bonds.
carbon-oxygen double bonds. Careful.
Oh, wait, why is it an asterisk?
There's an asterisk there.
Uh-oh.
Now, in reality, these are all sort of average values. If I replace one of these hydrogens with a fluorine, for example, would we expect these carbon hydrogens to have the same bond energy?
No.
Why not?
Because they have different.
The fluorine being highly electronegative is going to pull electron density away from this carbon. That's going to pull electron density away from each of these bonds, weakening those bonds. Okay? So we're not going to get exact numbers here, exactly what the same as we would get if we did a really good experiment. And part of the reason is the bond energy depends on the situation that that bond finds itself in. It depends on all the other neighboring atoms as well. Okay, so these are just going to be rough estimates for the change in energy for the reaction. Why is there an asterisk there? Because 745 is the most common bond energy for a carbon-oxygen double bond, but in CO2 it happens to be 799.
Oh, Lord.
It's down at the bottom. Now we're also making
It's negative, isn't it?
4 oxygen-hydrogen bonds. That's 4 times 467. Okay, so this is 1598. This is,
Oh god. Like 17.
somebody with a calculator,
1728, is that it? Oh, okay.
1868.
Yeah, I was on the way.
1868.
Dude, it's 249.
And when we add those energies together, we get what?
Additional.
3,466.
Okay, now the important thing is if we actually want to know what the overall change in energy is, we got to come back and think about the diagram that I just drew. Right? We are essentially taking CH4 bonds, pulling them out of that potential well. Well, we just calculated that that requires an input of 1,652 kilojoules of energy. We also have to take our oxygen-oxygen double bonds and pull those out of their potential well, which requires another 990. Okay? Now these are totals. I drew the dip for oxygen deeper because each oxygen bond is stronger than the carbon-hydrogen bonds. Okay?
Wait, but not by that much.
So I'm kind of doing total bond energy here. Or sorry, I'm doing individual bond energy here, whereas these numbers are the total bond energy. So I guess if I stacked 4 of these on top of each other, that overall change would be 1652. Okay? But the point is then when we make our products, we don't have to pull them out of the potential well. We've already pulled our atoms apart, now we're allowing them to come together. So now we're thinking about having our separate atoms and letting them come back together. I'm just going to draw it on this side. Okay, so to make our H2O and our CO2, we get back out 1598 kilojoules in making our CO2, and we get back out 1868 kilojoules when we make our H2O. So when we do this calculation to figure out what is the overall change in enthalpy from start to end, convention becomes important. We have to switch the sign for the making of the bonds because making bonds releases energy. Now we can add these together and figure out what is the overall change in energy for this reaction. Somebody with a calculator.
Oh.
Negative 824?
Yeah, that sounds right. No, like.
Okay. And that's kilojoules per mole of methane burned. Alright. Now a lot of times this diagram is not really the way we're going to represent this. We're still going to represent it on a potential energy diagram. We're just going to say that, okay, our CH4 and our 2O2s are here, and they require us to add 2,642 kilojoules of energy. What do we get when we do that? We get individual C's, we get individual H's, and we get individual O's. Then when we allow those things to react, we get a release of 3,466 kilojoules of energy to form our CO2 and our 2 H2Os.
So is the 2642 the like the activation energy?
Not necessarily.
Oh.
That would be the activation energy if this reaction actually occurred by the mechanism of pulling everything completely apart. Okay? So now Hess's law says it doesn't actually matter how I get from this to this. Conceptually, whether I figure out how much energy it takes to pull everything apart and then put it back together, that change in energy here should be the same as if some other multi-step process occurs, right? We don't actually have to know what the mechanism of this reaction is to calculate its change in energy. As long as we can come up with some
Proposed mechanism?
well, energetically, as long as we can come up with a pathway that leads us from the reactants to products, and we know the change in energy for that pathway, we can actually calculate the change in energy for the reaction. All we really care about is this. And that is going to be the energy of breaking the bonds minus the energy of forming the bonds, which we just calculated as negative 824 kilojoules. All right. Sometimes you'll see the equation delta H, the change in enthalpy, the change in potential energy for a reaction can be estimated by, oh my God, stop! You stop!
Oh,
Adding up.
that wasn't loud enough. I mean, it could have been a bit louder there.
I know, that was pretty good. Adding up the bond energies that we are breaking, so the bond energy of the reactants, and subtracting the sum of the bond energy of the products. Now this equation is confusing because it says reactants minus products, and if you look at your equation sheet, the third equation on the thermochemistry section says delta H. It has that same symbol, sum, but then it says products minus reactants. The third equation on thermochemistry of your equation sheet. That's not the same as this. We're going to talk about that one next. Okay, but that's a totally different equation. This is talking about bond energies. This other equation is talking about something else. Okay. The other way, sometimes people say, let's write it, bonds broken minus bonds formed. Let's add up the energy it takes to break the bonds. We'll subtract the energy that we get back out when we form our new bonds. That difference will give us the overall change for the reaction. Questions on that? Hope just woke up, so I'll give her a chance to let it soak in. Of course, she can always watch the fantastic YouTube video.
Great commentary.
Oh my God.
Any questions on this? A break?
There's a sink.